Our next speaker is Lior Zivan, who's the CTO of Eviation. He has been there for a year and a half. He has a Bachelor of Science in Aerospace Engineering from Technion IIT in Israel. He has 15 years of aircraft development experience working for IAI, the Israel Aerospace Industries, and he is an adjunct lecturer at the Faculty of Aerospace Engineering at Technion. Please welcome Lior.
I'm going to discuss a little bit about the aviation ALICE, and I'm going to look at the engineering perspective mostly. So I want to highlight the engineering challenges that were in our way to develop this new innovative all-electric aircraft. How do I switch slides? Okay. So let's meet the ALICE. It's a 9-passenger, 2-crew, 2,300 pounds payload capable with a max range of 540 nautical miles, plus IFR reserve of 45 minutes, of course, a cruise speed at 220 knots, a max speed of 260 knots, and currently limited to 12,500 feet due to non-pressurized cabin for the first version, but this is something that will come in the next versions. The stall speed is below 100 knots, and the takeoff distance enables the ALICE to operate from regional small fields. So our value proposition is, well, I think everybody in the room shares the same, more or less, value proposition. So we want to reduce the operating cost, to allow a clean operation without any CO2 emissions. And eventually, we want to reopen closed routes, make a regional transport by aviation a major player in how people commute, and enable people to travel much faster than today in a much comfortable ways, for the same or less cost. Okay. So how do we do it? Firstly, electric by design. If you will look at the platform, and I will carefully follow each feature later, you will see that it is not look like any other standard aircraft. And the reason is that it was designed for electrical propulsion system that has some limitations, of course, and on the other hand, a lot of opportunities that I will discuss as well. And secondly, we wanted to give a different user experience, something much comfortable, much nicer, much more modern than the current fleet, which is 40 to 50 years old, as already has been said in this room. So, meet the ALICE. For those of you who couldn't make it to Le Bourget, that's the ALICE. You can look that it has 3 propulsion units, a very sleek aerodynamic design and thin wings, a very nice, clean, white, modern interior, and a state-of-the-art glass cockpit with fly-by-wire system and side sticks, pedals. Unique displays due to the new feature that electrical propulsions enables, that I will explain later on in more details. So, what did we wanted to achieve? We wanted to achieve the range, firstly, at high speed, to capture the time of the travel, of course. And of course, the ease of piloting, again, going back to the pilot shortage and required training periods, so we wanted to keep it as simple as we can for the pilot, and of course, passenger comfort. And our way to do it was to have a highly coupled design, So all the different disciplines were very, very tightly coupled on one hand, and that makes this design a little bit complicated, of course. But on the other hand, you can take all the good things that comes out of those specific energy system, those specific propulsion units that have a lot of benefits and a lot of nice feature, and get back from the design a very, very capable platform with nowadays batteries. And I think that was our main goal, to meet the performance with the current available battery technology, not the one that we will have in 5 years and not the one that we will have in 10 years, the current technology. So, batteries. The first challenge is, of course, to get a high energy density batteries. So that's really, really a big challenge, but good for me, it is not my challenge. I do aircrafts. I know about batteries, I know about discharge rate, about the curves, about everything, but I'm not a chemist. I cannot help the humanity to improve the batteries. I'm sorry. All I can do is to design the aircraft as good as I can to get the performance with the current battery technology. So this is what we are trying to do. So battery density is a problem, not mine. Mechanical installation of thousands of cells, yes, it is my problem. Thermal management of those, indeed a problem. Discharge, charge, high altitude, low altitude, those have to be kept in more or less the same temperature to be efficient, and that was our problem. And besides that, battery management as a whole, state of charge. How much energy do I have? How far can I get with what I have now? What is my reserve time? Well, with fuel it's easy. It's a constant energy per gallon. But with batteries, it's not very easy. It varies with the temperature, it varies with the power consumption. So high discharge rate, you get less from the same battery. So that goes back to your flight pattern. So your flight pattern is affecting your fuel efficiency. And that goes to a nonlinear issues and nonlinear tables and a state of charge estimation that has to be correct, because otherwise you will end up with no energy and you won't reach your destination. And besides from that, that goes back to the pilot display. So how do you display battery? How do you display those new technologies to an experienced pilot in a way that he can understand and have situational awareness without a lot of simulator training? And we did try to keep it simple. Next, after batteries, aerodynamic efficiency. So we have 280, something like that, watt-hour per kilogram at the cell level. And we can probably do 240 at the pack level, and this is what we're doing. So we don't have a lot of energy. And the way to get those performance was by having this slick, totally clean aerodynamic design, no inlets anywhere on this platform. And we have a lifting fuselage, a lift-generating fuselage that takes about 20% of the lift, in addition to a very, very thin wing and the VTOL, which is very, very lightweight and efficient aerodynamically, but of course creates other problems in terms of flight control and redundancy that we have addressed. Wingtip mounted EPUs to reduce the wingtip vortices and reduce the overall induced drag. And the VTOL I've already discussed. So that was the main draft for this very non-conventional aircraft design. Propulsion. So we have those wingtip mounted EPU, and that's a cooling challenge because we don't want any inlets, because inlets are drag, and we are working very, very hard to maintain our lift over drag ratio of 25. So the entire cooling system was integrated in a conformal way to the skin, which is aluminum in the front. And that system is adding zero drag to the aircraft aircraft configuration. Those wingtip propulsion units, on one hand, generates counter-rotating vortices, so that's reduced the drag, but on the other hand, that generates new controllability issues. One engine inoperative. So what do you do when one engine cuts for some reason, although they are all dual, redundant all the way? Bird strike issues. So those were the things that we had to deal with in the development to make sure that we keep it safe. This unique propulsion unit distribution enables us, on the other hand, to make some new optimizations. Since the wingtip propulsion units are more efficient, since those are reducing the drag and also get some extra thrust from the virtual RPM because the induced vortices are rotating in a counter way to the propellers, can be optimized versus the aft motor. So the power distribution is not 33%, 33%, and 33%. It is more close to 40, 40, 20. So that enables another level optimization to get those performance from this kind of configuration. And once you go there, you are getting back to okay, now we have 3 motors. We are cruising. We are not doing nothing. 2 of those are at 40%, some RPM, some torque. The other one is with totally different numbers. And we have a pilot there. He looks into the dials and, well, do I have a problem or not? Is that normal or not? So that generates a new issue of how to display this properly to the pilot so he will know that this is the right way. And those optimizations are being done automatically according to the specific flight conditions. So when you take off, well, all 3 motors are at max, and then you go to cruise, and then the system starts to optimize that, and maybe the wingtips will get more power, and when you will go down just a little bit more, and when you go up just a little bit less. So those were new issues that we had to address in this platform design. Oops. Propulsion. Another slide about propulsion. Another big advantage of those electrical motors is that they have an almost flat torque curve. That means that you can get the torque at any RPM, not like any other engine or motor. So that enables 2 things. First of all, we have another feature because now we can totally decouple the RPM from the torque. So we can have the same power, which is the multiplication of RPM and torque. At few configurations, I can get 2,500 RPM and 1,000 Newton meter torque, and I can have 2,000 RPM and 1,200 Newton meter torque. Same power, but not same performance. So now the optimization is much more flexible. I can choose the exact RPM, exact torque for each flight condition, and this can be optimized following lookup tables in advance and real-time optimization while flying to keep the energy consumption to the minimum possible. And that will give the aircraft a little bit more range and a little bit more performance. Now, on the other hand, that enables us to control the noise amazingly. We can take the RPM down, we can take the torque up, we can pay with additional power. I agree, we need a little bit more power to do that. But once the RPM go down, and that's a 5-blade, by the way, Hartzell propeller, the sound goes deeply down. So the noise emissions can be controlled. At the same thrust, I can make it more noisy or more silent. So the pilot cannot do it, but he can choose, and this is this funny button here. It has range and silent mode. So if you are limited because you need to fly low over a populated area, then you can go silent. Well, you will pay with the range something, but you can reduce the noise emission dramatically. And you can even take off in this position as long as you have enough long runway. That will work as well. So you can operate at night and almost anywhere. So that's another new feature that electric propulsion enables. And the next one is that propulsion is not limited only to the propellers. So we are designing for in-hub motors for taxi. And except for the capability to go directly into a hangar and not be needed to have a tow car to take you in and let the passenger board in a closed, nice, cool or warm environment instead of the outside, this has the option also to pre-spin. And pre-spin is dramatic. If you can pre-spin your wheels to the same more or less velocity as they will get when you touch down, then, well, theoretically, no tire erosion at all. Nothing, zero. No rubber left on the runway. And that's one thing. And the other thing is that your spin-up and spring-back loads on the landing gears are dramatically reduced. And that's a big deal because I would say that a large amount of the carbon composite of the wing beams is there to support the spin-up and spring-back loads, not the bending due to aerodynamical loads. So if we can take credit for that, and for that we need the system to be high integrity, of course, because it has to be safe, et cetera, but this is doable. And then we can probably cut down something like 100 to 200 kgs of the aircraft weight, which means more batteries, which means more range. And a more nice experience for the passengers because it doesn't have this. You can feel that when you land. Weight. So yes, weight is definitely was a challenge. The entire aircraft structure is all composite, lightweight, state-of-the-art design because we had to keep it light. And the reason we had to keep it light is because we have 3.8 metric tons of batteries. So not a lot of weight potential for anything else. We have spoken about the pre-spin reduction, weight reduction opportunity that we will take advantage of at some state. Another side of the weight is, okay, we have the structure, but we have a lot of systems. Since this is a fly-by-wire aircraft, everything is driven by a computer or more accurately, a free triple redundant computer system that is, by the way, made by Honeywell. So when I had fly-by-wire computers in mind before this project, well, it was a cabinet, right? That's what fly-by-wire systems look like. But not this one. Not this one. Each of those small computers is less than 5 pounds. And the entire system can be installed here on my pad. That's amazing. And that's dramatic. And that's very, very important. One big enabler for us is to be able to have the system in this size, this weight, to be accommodated in a Part 23 aircraft. And I think that this is the first time that a fly-by-wire system is going into a Part 23 aircraft, a fully fly-by-wire system, everything fly-by-wire. System engineering, well, that's self-explanatory, I think. So we had to balance, that goes back to the holistic approach, we had to balance between everything and everything. But I want to address that. The entire system design was firstly built to safety. So that was the main drive. The entire fly-by-wire system is triply redundant. We don't have any single failure that can affect a safe flight. And even in cases of more severe failures or more than one failures, looking at the design of the wingtip propulsion units, we have redundancy. Amazingly, we have a VTOL. And each of the actuators is dual redundant and totally independent than the other half of the actuator. So we don't have a common main failure, and each of those have at least 2 communication channels with some of the fly-by-wire computers. So the odds for a failure there is very, very small. But even then, if you lose half a rudder vector, now your pitch is coupled with the yaw. And then you cannot fly. Well, you cannot fly if that was a conventional aircraft. But you have the wingtip propulsion units. They are already there for other reasons. So why not counter yaw with them and decouple that? And then you get back pitch control, yaw control, with one jammed actuator of the VTOL. And that's new. Nobody has done that before, as far as I know. And that's a new enabler that allows this platform to be safe while trying to optimize for performance and environmental impact and availability and price and everything else. So although it looks like those wingtip propulsion units are generating problems, they are also generating a lot of new opportunities because we can use them to do something that hasn't been done before. And that was our challenge, to have a very, very highly coupled, holistic design approach that will take the current technology and bring us to where we want to be in terms of speed, range, cost, and comfort. Of course, we could not have done it alone. We had great partners for this project, from global aviation leaders that were actually part of the team. I mean, and I'm saying part of the team, they were part of the team. They were with us in the integration at France. They were with us from the first day to the last day, and some of them were with us when we assembled the aircraft at the Paris Air Show under the sun. So we had great partners here, Siemens, now Rolls-Royce, for one set of propulsion system, and Magni-X for an alternative one. Both of them are doing a great job. They have great propulsion units. Honeywell, Lord, Maniagi Aeronautica, Hartzell, Bendix, King, Carboman Group, which supported us with the integration of the aircraft, Hartzell Propeller, of course, Lord for the pilot inceptors, Alma Design for the great, great, great interior. We had great partners for this project. So how do you assemble an aircraft in 3.5 months? So that's the way. You do it with a lot of good partners, with a great team, and with a lot of coffee. A lot of coffee, trust me. And that was done in France. The fuselage manufacturing was done in France. All the other parts came from something like 21 countries from all around the world. And we have done the integration there and then shipped that amazingly looking Alice to the Paris Air Show. So what's next? So now as we speak, the aircraft is currently somewhere in the Atlantic Ocean on its way to the States. And the first aircraft, the Paris Air Show aircraft that's in the picture, is going to get to Prescott, Arizona for system testing mostly before first flight. And we have Honeywell close support at Deer Valley, which is not far away. So that's a good place to go with the system testing. And afterwards, this bird is going to get to Moses Lake for flight testing. And by the way, in parallel, we are building the next one already. So we will have hopefully, two aircraft we can test flight to expedite the flight test period. And except for that, we have started our certification process hand in hand with the system testing, second Alice production, and a long period of flight testing that's ahead of us. That's all. Thank you very much.